Welcome. Good Saturday morning or afternoon, or Sunday morning or afternoon or evening, whenever you're watching this. This video is going to be about slant asymptotes and a continuation of our discussion on rational functions. Namely, how do you graph rational functions? How do you figure out the features of a rational function, including its domain, asymptotes, kind of like x-intercepts, crossings of the x-axis, and just the general shape of it. And we've found a lot, we found that rational functions can have very difficult to graph. The graphs can be very challenging to draw because they have lots of different flavors. They look different depending on the zeros of the numerator and the zeros of the denominator. And yeah, so basically graphing rational functions, each one is a little puzzle to figure out. Okay, so the learning objectives in this lesson are to find the slant asymptote of a rational function, also to know when rational functions will have slant asymptotes, and then to graph a rational function including its slant asymptote. We'll hit those things that we did last week with just graphing rational functions with horizontal asymptotes. We'll just include a slant asymptote for these. So first, what is a slant asymptote? A slant asymptote is a line with non-zero slope that the graph will approach. And it's, again, an end behavior thing, so it's free to cross the slant asymptote in the center of the graph. It's just, this is what the line will approach as you go off to infinity to the left or to the right. And the feature of a slant asymptote that's different from the ones we were looking at before, horizontal asymptotes, is that slant asymptotes are linear equations that don't have a slope of 0. So the previous ones, our slopes were 0. There was some horizontal line, could be at 0 if the degree of the denominator is greater, or some other value if they had the same degree. And so it was a flat line. There was no slope to it. Slant asymptotes are going to be lines with some slope, positive or negative, okay? Rational functions will have slant asymptotes when the degree of the numerator, that's the polynomial on top, is 1 more than the degree of the denominator. And strictly 1. So we're only going to get slant asymptotes when you've got like a cubic divided by a quadratic, or you've got a 4th degree polynomial divided by a cubic, a 3rd degree polynomial. Those will be the times where you're going to get slant asymptotes, okay? So for example, x squared minus 4 over x plus 1 will have a slant asymptote because we have the degree on top, which is 2, a degree on top, we have degree 2, and we have a degree 1. And so previously, all we knew about this was its end behavior. Its end behavior in this case, if you look at that ratio, it's going to have the same end behavior as x, which is, as you go left, you go down, and as you go right, you go up. So it will have that end behavior to it. But now we know exactly what line this thing will approach, or we're going to find that out in this lesson. What's the line that x squared minus 4 over x plus 1 approaches? And so let's just look at its graph, and we can see what the slant asymptote is. We can at least attempt to find it. So here's the graph of x squared minus 4 over x plus 1. I'm going to go down here. So we have x squared minus 4 over x plus 1. And I was able to figure this out, and we'll do this together in a minute, that the slant asymptote is the line x minus 1. So y equals x minus 1 is graphed in black, the black dashed line. And if we're to zoom way out, let's get this graph looking in projector mode. So if we zoom way out, we can see that the rational function approaches this line very nicely, the line y equals x minus 1. And if we were to, say, look at it at 100, if we were to, it's barely distinguishable, right? It's just below that line y equals x minus 1, okay? So that's our slant asymptote. Now you can find the other features of the graph pretty the same way we've done in the past. look for zeros of the numerator. That's going to tell you these points, negative 2 and 2. Look for zeros of the denominator. That's going to tell you this, vertical asymptote. So we're going to do the same things we did last week, which is finding all those special features of the graph, x and y intercepts, and vertical asymptotes. But then we're going to have to find the slant asymptote as well. All right, so how do we do that? Or I guess you could ask the question, why does this even have a slant asymptote? Why does it approach that line? So to see why, we're going to go ahead and do one thing we did 2 weeks ago, which was polynomial division, where we take our rational, which is x squared minus 4 divided by x plus 1, and we rewrite it. And so if we rewrite it using polynomial division, then we're going to get something that looks like this. X minus 1 minus 3 divided by x plus 1. I'll just go ahead and do it real quick so that we are refreshed. And how do we do the polynomial division? We put our numerator x squared minus 4. I'm going to put 0x in there as well so I don't lose track. X squared plus 0x minus 4 underneath the division symbol. And then we put our denominator x plus 1 out in front because that's what's dividing it. It's our divisor. Now we're going to go ahead and figure out what do I need to multiply x by to get x squared, and that's x. So we have x squared, x times 1 is plus x. Subtract. 0 minus x is minus x. Bring the minus 4 down if you so choose. X times negative 1, that's minus 1. So we have minus x minus 1, subtract. Then we have negative 4 plus 1, this is minus 3. That's the remainder. That's g, the quotient. So we have x minus 1 minus 3 over x plus 1. And so if we look at this, we can see the slant asymptote is there. That line, y equals x minus 1, is right here. It's the g part of the polynomial, of the rational function. So whatever our linear part is after we do this division, and when the degree of the top is 1 more than the degree of the bottom, you're always going to end up with some linear function, linear polynomial in front. That's going to be our slant asymptote. And why is this the case? Why does it approach x minus 1 when we plug in really big x's? Well, if we plug a large value in, large x value, then it's going to look like x minus 1, that value we plugged in, minus 3 divided by something huge. So that 3 over huge is really a tiny number. So this part here is really going to be a very small number after we get big enough with our x's. And we don't have to go that far out for this number to be very small. So for example, if we wanted to evaluate this function at 1,000, right, this is pretty far out to the right on our x-axis. If we plug 1,000 in, now I could plug it into the original function x squared minus 4 over x plus 1, or I could plug it into the one on the right. I'm going to go ahead and use the one on the right because it's really going to illustrate the point of what's going on here, where we have some number minus something very small. Well, we have 1,000 minus 1 after we plug in 1,000 for x, and that's 999. And then we take away 3 divided by 1,001, so minus 3 over 1,001. And if you subtract 3 divided by 1,001 from a number, 999 in this case, turns out that barely changes it, right? This is actually 998.997. So it's really close to 999. So it approaches that value. It doesn't equal 999, but it's very, very close to 999, which is the value x minus 1. Okay, so that's why we're getting close to x minus 1. We plug in something that's very big, that remainder part goes to 0, and we're left with that rational, or that linear function as what we get what we're close to. Okay, so to determine a slant asymptote, if you've got a rational function where the degree of the top is 1 more than the degree of the bottom, so degree of p is equal to degree of q plus 1, it's going to have a slant asymptote, and you just have to find it. To determine it, you're going to rewrite p over q as g plus r over q using polynomial long division. And the slant asymptote is going to be g. That's it. So that's all there is to it. And then everything else we've talked about already. We've already talked about how to find x and y intercepts, vertical asymptotes, and so forth. So we're just going to sketch those like usual. Alright, so if you understand this from here, I'm going to run through a couple of examples. You're going to get some example practice with this next week as well, so in class starting on Monday. So I guess if you feel like that's enough, like you've basically learned it, and now you just need to practice it yourself, you can stop the video now. If you want to watch through some examples, then I'm going to go ahead and run through them. They'll take a little while each because there's a lot to do for each problem. But I have 3 examples set up. Yeah, so stay tuned for some examples. Okay, so we're going to sketch the graph of this rational function, x squared plus 5x plus 4 divided by x plus 2. Now this is going to have a slant asymptote because we've got a degree 2 over a degree 1. And so since the numerator is 1 higher, we're going to end up with a slant asymptote. Here I've got my graph set up over here on the right. I'm going to go back up to the upper left corner. Okay, so I have a graph. My graph is set up over here. We're going to sketch each feature as we go. So first and foremost, you always want to start off these problems by factoring. So we're going to factor the numerator and the denominator so that we know off the bat what our x, y intercepts and any holes. X plus 4, x plus 1. Yeah. So factoring the numerator, we get x plus 4, x plus 1 over x plus 2. We see nothing is common on top and on bottom, so there's no holes. Nothing will cancel. We have a vertical asymptote when x is equal to -2. So I'll use another color. And there's no holes because no common factors. Now we'll determine the x and y intercepts. Well, those are pretty simple as well. Our x-intercept is going to be, x-intercepts are going to be zeros at the top, zeros of p. So we look at the numerator and we see -4, 0, and -1, 0 are going to give us x-intercepts. And our y-intercept would be evaluating the function at 0. So if we take the original function, which now I can't see, sorry, we take the original function, we plug 0, and we get 0 plus 0 plus 4 over 0 plus 2, which is just the number 4 over 2, which is 2. So that's our y-intercept. We've got our y-intercept, we've got our x-intercepts, we've got a vertical asymptote. All right. So we're going to sketch each of these on our graph. We'll start off with the vertical asymptote at -2. So here we go. That's not very clear. Let's use another color. I like red. Okay, red. There's our vertical asymptote. Okay, we're going to go ahead and plot each of these intercepts. Let's use purple. Let's use purple for our graph. So our x-intercepts are at -4, 0. And -1, 0, so right there and there. And we have a y-intercept at 0, 2. Perfect. Alright, so already we can see some features of this graph. We know it's probably going to go down towards infinity over here on the right side. So it's probably going to go down towards infinity here. And it's likely going to go up towards infinity over here. The reason why it probably doesn't go up over here to infinity is because we have to have this intercept 0, 2, and so if it were to do that, it would do some weird curvy thing where it bounces down and then goes up, and that seems unlikely. It probably just keeps following this down this way. All right. So the next step is to determine the slant asymptote, and so we're going to do polynomial division. X squared plus 5x plus 4 divided by x plus 2. So we have x squared. Let's use a better color. Divided by x plus 2. So we're going to do our polynomial division. We have x squared. We only have one or two steps to go to figure this out. And we get 5 minus 2x. That's going to be 3x plus 4. x into 3x is plus 3 times. So x times 3, that's 3x. Oops, running out of space. Plus 6. Go away. Keep. Oh, lost it. Okay, where were we? We're at 3 and 6. So that's 6 plus 6. And we subtract that. We have 4. Oh no. Oh no. 4 minus 6, that's minus 2. Minus 2. So we have our rational function now. This is our remainder. It's been rewritten. We have x plus 3. And so that's going to be the same as what f of x is. It is exactly equal to x plus 3 minus 2 over x plus 2. And so let's go ahead and plot that slant asymptote, which is the polynomial part of this quotient. So we have x plus 3. So that means we have a y-intercept at 3, and our slope is 1. So I'm going to just start plotting those points, and then we're going to use a dashed line to represent it. So something like this. Yep. So there's our slant asymptote. And so that's going to be the line our function approaches as we go to the left. So we go to the left, and as we go to the right, we're going to get closer and closer to this line. So, oh, it looks like, yeah, that's what we had said earlier. It doesn't make sense for this point, you know, at negative 1, 0, for the graph to zoom up, right? It doesn't make sense for it to zoom up. It makes more sense for it to zoom down, because otherwise it would have to do some weird U-y thing right here. So we can see, based off of this part, that it does approach that line in this nice way. And as we curve down towards negative 1, 0, it would be very bizarre for it to zoom up. We could do sign analysis and just check on either side of that asymptote negative 2. I guess I'll do that for just to you know, be doubly certain that it does in fact go down. So I'm like 99% certain it goes down like this. Let's go ahead and just do that so that we can make sure for ourselves. So we're going to look at negative 1.9. So if we plug negative 1.9 in, we're going to get negative 1.9. Oops. Negative 1.9 plus 4. Negative 1.9 plus 1. Negative 1.9 plus 2. So if we take a look at each of these values, we have a positive. So we have negative 1.9 plus 4 is plus. Negative 1.9 plus 1 is minus. Negative 1.9 plus 2 is plus. So we have overall a negative. So just to the left, or excuse me, just to the right of negative 2, we're going down to negative infinity, as we expected. And we'd find that if we did the same thing on the left side of negative 2, we're going up to positive infinity. So we're going to go through that point and up. Now make sure that your graphs actually do contain the x and y intercepts. That's the whole point of finding those points, is it gives shape to the graph, right? So we have, it helps you graph because it gives you some points to plot. You know the curve has to pass through those points. So 0, 2 is one of the points on our graph. Negative 1, 0 is another point on our graph. And negative 4, 0 is a third point on our graph. So it gives us some nice things to test. Okay, there's our graph. Let's see how well we did. So we're going to go ahead and go into Desmos and sketch x squared plus 5x plus 4 over x plus 2. All right, so looks like we got those same points that I mentioned earlier, 0, 2, negative 1, 0, and 4, 1. And my graph is all kind of skewed because there's more pixels left, right than there are up, down. But anyway, we can see this line x plus 3 is our asymptote, as we found earlier, right? The line y equals x plus 3. Let's see if I can't just, there we go. That looks a little bit better. And we zoom up to infinity as we approach this vertical asymptote on the left, and we go down towards negative infinity as we approach this vertical asymptote on the right. And so there's our graph. It's a nice little, curvy, it's a slanted rational function. Okay. All right, so let's do another example. So again, if you feel like, okay, that was good, you can stop the video now. If you want another example, then keep going. Okay, example 2. We're going to sketch the graph of the following rational function, x to the 4th minus 16 over x cubed plus 8. So x cubed plus 8 and x to the 4th minus 16 can be factored. So that's always going to be our first step. Remember, we want to factor these two guys out. So if we factor the numerator, we're going to get x squared minus 4, x squared plus 4. And then if we factor the denominator, we're going to get x plus 2 squared minus 2x, whoops, running out of space. Okay, so that's what it factors to, x squared minus 4, x squared plus 4 over x plus 2, x squared minus 2x plus 4. But we notice that there's another difference of perfect squares in the numerator. X squared minus 4 factors again into x plus 2, x minus 2, x squared plus 4. And our denominator has a factor of x plus 2 as well, squared minus 2x plus 4. The denominator is a sum of perfect cubes, so that's a formula that's in your notes. You can go ahead and find it again. It's a plus b times a squared minus ab plus b squared. So it's just a formula. You plug it in, test it out if you're not sure. And we see that there's a canceling common factor. X plus 2 cancels from the top and the bottom, so we're going to end up with a whole. So determining vertical asymptotes and wholes, there's no vertical asymptote in this case because we cancel what would make the denominator 0, and this has no zeros. So that that quadratic that's left over after doing the difference of sum of cubes formula doesn't have any zeros. So we're going to have no vertical asymptotes. We will have a whole, and the whole is going to be at negative 2, negative 8 over 3. So negative 2 we can see because that's the 0, of the common factor. Negative 8 over 3, that's going to be from plugging in, if you plug negative 2 into the simplified version. So we plug negative 2 into the top and the bottom, we get negative 2 minus 2, 4 plus 4, that's negative 2 squared. And then we have 4, negative 2 times negative 2 is 4 plus 4. So if we were to simplify this all out, we get, this is minus 2 minus 2, so this is negative 4 times 8 over 4 times 3. There's 3 of them. And so that would end up being negative 8/3. Okay, so that's our y value for the whole. And so we continue on our quest, finding the x and y intercepts. So our x-intercept is going to be what makes the numerator 0. And in that case, we have just 2. So just this guy. X squared plus 4 can't be 0. So we have 2 as one of our x-intercepts. Our y-intercept would be from looking at the constants. So that's 0 minus 16 over 0 plus 8. And this is negative 16 over 8, which is negative 2. So that's our y-intercept. So, and then we're going to find the slant asymptote by doing long division. So I will spare you doing the long division in front of you. Just know that's what you end up getting. X minus 8x plus 16 over x cubed plus 8. And now we just plot each feature on the graph. So we'll start off by doing our asymptotes. No vertical asymptote. We have a slant asymptote. And so we're going to sketch the slant asymptote. It's just the line y equals x. So, do my best. So there's our slant asymptote, the line y equals x. And then we're going to plot those points that we found from earlier. So we have points at, let's use green. I like a green graph. So our points we found was that 2, 0 was an x-intercept, so we have this point here, 2, 0. We found y-intercept was at 0, -2, so right there. And we found a hole at -2, -2.666. So that's over here. There's a hole in the graph, right around -2, -2.6. And so it looks like we don't have any vertical asymptotes, so we just have to kind of connect the dots in a nice smooth curve and have it go towards that asymptote. So if we were to have this point connect and go towards that asymptote, it would look something like this. We need these points to go towards that asymptote, so it's going to look something like that. And then we have to connect these guys in the middle. Well, it's probably going to do something funky like connect, I don't know, some way like this. Let me erase this a little bit. So we need these guys to connect. Now it's going to be nice and smooth. There's no straight line connecting those points. Everything is curving some way. And if you want, you can actually plug in this value. You can plug 1 in and see what the answer would be. If you were to plug 1 in, you get 1 minus 16 over 1 plus 8. And that's -15 over 9, which if you calculate that, I believe, what's -15 over 9? Well, let's just look at the graph because I have it set up over here. So yeah, there's our function. There we go. Okay, so if you were to plug 1 in, you would get something right around here, -1.6. So I think that's good enough for this video. We'll go ahead and look at some more examples in the next video, and just in time. Say hi, Mushy. Okay. All right, I'll see you guys on Monday.